where we ended. Okay, last time we met. So I explained. Okay, anyway, we discussed everything last time. So we go direct to the example. So internal energy. Calculate the internal energy of a system undergoing an endothermic process in which 15 point kJ or kilojoules of heat flows and where 1.4 kilojoules of work is done on the system. So first of all, you want to ask yourself, remember you're looking at internal energy, the energy that the system has. So you are looking at, if this is an endothermic process, then where is the heat going? Is the heat going to the energy, sorry, is the heat going to the system or out of the system? It's going into the system, so meaning the heat is going to, that value is going to be a positive value, remember that. Then they say 1.4 kilojoule of work is done on the system. If you are doing work on something, then the work is going to be positive. Okay, if you are doing work on the system, the work is positive. If the system is doing work on the environment, the work is going to be negative. Okay, when you work, you don't feel refreshed now, do you? No, you don't. Rather, you feel tired and you have to rest because energy is flowing out of you, right? So that's how we could look at it, like I explained last time. So, having talked about that, it's really relatively straightforward. So, like we explained last time we met, to say the change in internal energy is heat plus work. So we said our heat is going to be positive because this is what? This is an endothermic process, right? So it's going to be positive 15.6 kilojoule. Then the work is going to be, so plus, so the work is going to be positive as well because work is being done where? On the system. So you're going to have, this is going to be 17.0 kilojoules. So you see that? So there you have it. So there you have it. Yeah. So that's our answer. That's our answer. Nothing complicated now, right? Okay. So now we now go a step further and we are now going to talk about how we can then relate the work being done by what? Pressure. And I love the way we've moved because we are talking about pressure in physics and also in mathematics and also in chemistry. So I think it will be easy for us to appreciate this. So now, a common type of work that's associated with chemical processes is work done by a gas, right? So this is could be work done by a gas, so through expansion, right? So maybe it so happens that when the gas expands, it's moving something. Okay, so maybe you could find that maybe when the gas expands, it then moves. Remember those pistons of how the car moves, remember, right? Like how the gas will expand and then it moves the piston in an automobile or in a vehicle engine, right? So the gas expands and it moves the pistons and the car eventually moves, right? So work is being done by what? By a gas. So usually expansion or an increase in the volume of the gas is usually associated with what? With work being done by the gas. Okay, so that's an important point to take note of. And then when work is done on a gas, that's compression. You don't expect a gas to just compress itself out of the blues, nah? Yeah, so you don't expect that. So what happens is that there is going to be the what can I say? So there is going to be the compression. When that compression happens, it's what? It's an external force. So it's work being done on a gas. That's why if you were to get a bottle, like that example that I gave last time, where we would play with certain bottles that had loose lids, and then would press them, would compress the gases, and the lid would pop out of the bottle, right? Or pop on top, out of the top of the bottle. So that used to happen, right? And that was because we are doing work on the gas. We are trying to what? to compress the gas. So now we can now be able to relate the work, the pressure, and of course the change in what? The change in volume. So what we are basically going to look at, we know what pressure is because we've just been doing it in physics. Huh? So pressure of course is force over what? Over area. Now we know something about work. What is work? Work is what? Work is force applied over a distance, right? So that's work. Or that's what work is. Huh? So it's just force applied over a distance. That's why you say force is equals to what? Sorry, work rather. Work is equals to force times the distance. Now, what is this distance? So look at on your far left. You are seeing that piston that we were talking about, right? So that piston has been moved by a certain height, isn't it? So now we can take that height and say that particular height, that's our distance. Okay, so that particular height, the change in the height, the height which this piston was moved from the initial to the final state, we take that as a what? As our distance. And then of course we have our force there. Okay, so that's okay, isn't it? Okay, so our work is now being defined as what? As work is equals to force times what? Times the change in the height. Now, since we are talking about the gas, so what's going to be our force? Now we know that pressure is equals to force over area. So it means that if I want to make force the subject of the formula, it's what? It's force is going to be pressure times area. So now in that equation, which was work is equals to force times the change in height squared. So what we are saying is okay, let's just wrap this. So what we are saying is that we said work is equals to what? So we said work is equals to force times distance, right? But we know that in this particular piston, the distance is the change in the height. Now, we know that this is involving a gas, right? So this particular force, we know that it's coming from pressure, right? The pressure increases or pressure changes in the gas. So making force the subject of the formula is going to be what? Pressure times what? Times area. So I mean you can now substitute and say the work is actually going to be pressure times what? Times area times the change in what? Times the change in the height. Okay, so I hope you're able to see this relation, right? So that's done and done. Now, okay, yeah, so that's done and done. Now, there is something that's interesting here. You know that when you multiply area, okay, so you know that when you multiply area with the height, what do you get? You get volume, isn't it? Now, here this is the change in height, right? So you're saying the change in volume is equals to area times what? Times the change in height. So this means that your work is going to be pressure times the change in what? The change in volume. Okay, so that's how we come up with that equation. So we know that change in volume is just the final volume minus the what? Minus the initial volume. So that's basically that. So yeah, so I hope now we can see where our equation comes to be. Work is equals to pressure times or times the what? Times the change in volume. So now we're now going to think about what signs then are we going to put into this our equation. So what signs are we going to put for what for what? So the key thing is this. What about, so let's now talk about the sign of for work, huh? Because we've talked about the sign for heat and everything. So the gas, so if the system is expanding, okay, we know that the what? We know that the system is doing work on the surroundings, right? So what's going to happen is it's doing work on the surroundings. So we know that if it's doing work on the surroundings, well, what's happening? It's losing energy, isn't it? So meaning, like we said earlier on, so meaning work should be negative, isn't it? So meaning when there is expansion, the work is negative. So for an expanding gas, the change in volume is going to be positive. Now, why is the change in volume going to be positive for that. It's because it's expanding. So the final volume is what is greater than what than the initial volume, right? Okay, so what this entails is that therefore the change in volume and work have opposite signs, meaning when the change in volume is positive, there is expansion, then there is work which is being done by the system on the surroundings, isn't it? But then if you've got where the change in the volume becomes a negative value, it means that there was compression. If there was compression, it means that work has actually been done where work has actually been done on the system. Okay, so it's going to be a positive. So that's why we are adding that negative to our formula, so that if the change in volume is negative, so it's going to be negative, the negative in front times the pressure times the change in volume, which will be a negative. So then we are going to have a positive work, which entails that indeed work was being done on the system, and therefore it was compressed. Okay, so now let's now look at a practical question. So from what we've discussed, so now that's the question. So calculate the work associated with the expansion of a gas from 46 to 64 liters at constant external pressure. Okay, so constant external. So you see there the pressure is usually constant, right? There's no change in the pressure even from our equation. So that's basically about it. So then, yeah, at a constant external pressure of 15 atmosphere. So what you're going to do there is to say uh, work work is minus pressure, then changing volume. So you're going to have, they've told us that there is constant pressure of what? Of 15 atmosphere. Then the change in that, so we're going to have what? 64 liters minus 46 liters. So then what you're going to have is uh okay, so we are going to have that. So meaning what we are going to have is negative 270 liter atmospheres, right? So that's what you're having there. And so this makes sense because you see that this is expanding, so meaning it's doing work on the surrounding. Therefore, the work is what? The work is negative because this change in volume was what? Was positive. Because this change in volume was what? Was negative. Oh, sorry, was positive. Sorry, pardon me. So was positive, right? So that's pretty much about it. So that's how you would want to go about it. Okay. The negative, that's just part, that's what I was explaining to say the negative comes in from the understanding that if a system is to do work on the surroundings, the work has to be a negative. So this change in volume for a gas to do work on the surroundings, the change in the volume has to be a positive, right? Now we know that if we didn't have the negative sign, okay, if we didn't have the negative sign in the formula, it would mean that since the pressure is constant, right? But if we didn't have the negative sign, it means that if the change in volume is a positive for an expanding gas, the work would be positive, which would be a lie. Because we know that when a system is doing work on the environment, like we discussed over the last sessions, to say the work has to be negative. So it's conventional. So that our thermodynamic principles don't conflict with one another. You get it, right? Okay. So yeah, so that's about it. So then we now go to the hello, has your question been answered? Okay. Okay, so yeah, so that's the thing. That's what I was explaining before we went to that topic. I was explaining to say it's it's just convention. Because when something expands, it does work, and we know that work has to be negative. But if something expands, its change in volume is going to be positive. So if we didn't have that negative in front, then it means that our work will be positive, which would be a lie, because we know that work is positive when the system is actually gaining, or when work is being done on the system, right? And not the other way around. Okay. So now now look at since here we just made use of the work. So now in this other question, we are going to make use of the internal energy, heat, and work, and just to see how we can be able to combine all these things really. How we can be able to combine all these things and be able to make sense out of them. So a balloon is inflated to its full extent by heating the air inside it. In the final stages of this process, the volume of the balloon changes from that. Okay, so from 4 times 10 to power 6 liters to 4.5 times 10 to power 6 liters by the addition of 1.3 times 10 to power 8 joules of energy as heat. So addition, right? So meaning they were adding heat to this system. Assuming that the balloon expands against a constant pressure of 1 atmosphere. So that's just atmosphere, normal atmospheric pressure, right? Of the air. Calculate the internal energy for the process. Then a hint to convert between liter times atmosphere and joule. You use the conversion. 1 liter times atmosphere is equals to 101.3 joules. So that question may seem to be complex, but the best way you want to look at it is always ask yourself, what have I been asked to find? So the question wants us to find the what? Wants us to find the internal energy, or the change in internal energy. So what are we going to use? We are going to use the what? We are going to use this formula. So what do we know from this formula? What do we know? What have we been given? The Q, we know that they were adding what? This amount of energy. So they were adding, and it's positive, right? Because they were adding this energy. So they were adding this energy to the system. Then now what are we left with? Work. So now here what we have to calculate is to calculate our work, and then just add it to the what? To the heat. So now, because we know that we are talking about a gas that's expanding, so we know that here we are going to talk about what? Work, which is going to have minus. Again, this is just conventional like that. So that's our formula, right? So uh we know about the pressures which were involved. So -1, we put it, if you want just say negative. So negative, and then we've got 1 atmosphere, that's the pressure. Then the change in volume, it's 4.5 times 6 liters minus 4 point that, and then that's going to be that, right? So then what then you're going to do is, so you're going to find your answer to be minus. Okay, so again now you see this makes sense because, okay, just give me a moment. So this makes sense because we see that the gas is what? The gas is expanding and the work is negative, because we know that when something expands, even what happens in the vehicle, there are gases that expand. That's what moves the what? That's what moves the pistons, and the car will be able to move, right? So the work is negative because the system is losing what? Is losing energy. So I hope that adds up, right? So now we know that now this, look at the heat that we have is in joules, but the work that we have is in liters atmosphere. So we want to convert this liter and atmosphere into joules. And then once we convert it, that's when now we can say then add the two, right? So what we are going to do then is just a conversion, huh? So usually when there is something to convert, don't make shortcuts, because sometimes you can end up what you can end up losing marks, huh? So please always ensure that you show the conversion. So you do this. So that's 5.9. Then atmosphere. Oh, sorry. Let's write it better. It's a little bit long, so I'll start it from here. So that's that. So liters what? So liters atmosphere. So liters atmosphere. Then we were solving for x, right? So what is just happening is we're just cross multiplying, right? Okay, let me put all the units so that we can see how the units are canceling themselves. So we can see how the units are canceling themselves. So how these units are cancelling themselves. So liter atmosphere. So atmosphere. Okay. So then what then you're going to do is, of course, if you want, you can put the one that was there, but you know anyway it's one. So even if you leave it out, it doesn't affect anything, right? So you do that, right? So you cancel that, you cancel that. Then you're going to have x. So the conversion is going to be negative 5.1 times 10 to power 7 joules. Okay, so then you can now get this and then add. Then you can now use the formula to say internal energy is what? Q plus W. And then what you're going to have is, so you're going to have positive 1.3 times 8. Okay, so joules. And then now your work is what? Your work was negative, right? So that's about it, right? So once you do that, you're going to get your answer to be that. Okay, so you're going to have your answer to be that. So the point, so you see, the question looks so complex before starting it, but once you just take it step by step by step, you see that it's actually less complex than it actually looks. Okay, so that's an important point to take note of. Okay, so now let's now talk about enthalpy and calorimetry. So uh, we've talked about internal energy of a system, and so let's now talk about a certain property of a system, which is what we call the enthalpy, right? So what is enthalpy? So enthalpy is just what the internal energy of a system, uh, the pressure of the system, and the volume of the system. So practically, okay, I know this looks complex, but just look at it like this. Enthalpy is the H, right? Then the E we know is the internal energy of the system. Then pressure of the system times volume. That's the same as the work that we were finding, isn't it? Remember we said work for a gas is what? Is going to be minus uh, pressure and multiply by change in volume, isn't it? That's it, right? Exactly. So that's how you can look at it there. And now we are now about to start talking about what someone had asked when we had started about the state function, right? Okay, so that's pretty much about it. So, so since internal energy, pressure, and volume are all state functions, enthalpy is also a what? A state function. So what this basically means is that uh, what this basically means that a change in enthalpy does not depend on the pathway between two states. So basically, when you are looking at these things, the values in the enthalpy do not depend on the pathway. For it is just what is the internal energy, what is the pressure, what is the volume. Okay, so those are going to be there dependent on what. It doesn't matter whether what you are using to expand, whether you are using a hand, whether you are using whatever, so long as the internal energy is what it is, the pressure is what it is, the volume is what it is, even the enthalpy is what is going to be what, to be a state function. So that's really, so it's just a fancy way of just saying pretty much what I have said. Okay, so that's something that's important to take note of. So uh so that's something that's very, very important. So examples of state functions, you've got mass, pressure, density, entropy. So these just help us to simplify our calculations and see the change between the value, or sorry, yeah, and see the change in the value between the final and initial position, also known as state change. Okay, so a state function is a property that describes a particular state without depending on the path taken to reach this state. So the reason why I'm asked why I wanted to define it is because there was someone that had asked. There was someone that had asked on it. So that's why I wanted to ensure that I answer their question. So that's basically about it, right? So we've looked at at the formula that we had derived, and then so let's just see how really they broke down this into this part. Yeah. So uh we know that internal energy is equals to what? So remember that when we'll be deriving enthalpy, we are going to look at a process that's carried at constant pressure, okay? And where the only work being done is what? Is pressure volume work. So what this basically means is that the work that we are getting, since the pressure is constant, it means that where are we going to get our work from? Our work is going to come from the change in the what? The change in the volume. Okay, so if the pressure is the same, but then you are getting work, so it simply means that the work is coming from what? From the change in pressure. Oh, sorry, pardon me, from the change in volume. Okay, so the internal energy is equal to what? So we are looking at the first equation there on top, right? So under the conditions where the pressure is constant, we know that the internal energy is equals to what? Internal energy at constant pressure, that's what the QP means, plus work. So we know work of a gas is, we know it's a minus pressure and the change in volume. Or if you want, you can make the heat at constant pressure to be the subject of the formula. Then you are going to see that it's going to be the heat at constant pressure is equals to change in internal energy plus pressure uh, multiplied by change in volume. So now we now want to relate this heat at constant pressure to a change in what? In enthalpy. So remember, the definition of enthalpy is what? Is equal to internal energy plus pressure times volume. So then what we can now, we want to find out the change in enthalpy. So the change in enthalpy, uh, to find it, you are just basically putting the changes in everything, right? So you are saying change in enthalpy is equal to change in internal energy, change in what? In PV, which is pressure or volume. Okay, but since we know that the volume is what? Sorry, we know that the volume is the only thing changing and the pressure is constant. So that's why we've rewritten and said it's the change in enthalpy equal to the change in internal energy plus pressure is constant. So we just write P and then the change in what? The change in volume. Now you realize that what we've derived for the enthalpy change And what we had found for the heat energy at constant pressure is the same. Okay, so now this is very, very important because it tells us that the change in enthalpy is equal to the heat at constant pressure. Okay, so the change in enthalpy, so at constant pressure, the change in enthalpy of a system is equal to the energy flow as heat. This means that for a reaction started at constant pressure, the flow of heat of the change sorry the flow of heat is a measure of the change in enthalpy for the system. So depending on how the heat is flowing, that is actually giving you the enthalpy change that's actually occurring for that particular reaction. Okay, so because of this, that's why you could say the heat of the reaction or the change in reaction, right? So long as the reactions that are in question are talking about what? Are talking about a reaction occurring at constant pressure. Because it's only at constant pressure where this relationship holds true. So the enthalpy change, how do you find the enthalpy change? What you're basically saying is that the enthalpy of the products and the enthalpy of the reactant. So you're just saying enthalpy of products minus enthalpy of reactants. Okay, pardon me. Okay, so that's that, right? So mm, remember, we are talking about energy flow, right? So uh, if the enthalpy of the product is greater than the enthalpy of the reaction of the reactant, it means that the products have got more energy than the reactants. So then where did they get the energy from? It means that first of all, you know, the enthalpy change will be positive, but where did they get the energy from? It means that the energy was absorbed by the system from the surroundings, isn't it? So it means that the reaction is what is endothermic. So here you don't have to memorize. Say no, it's changing positive. No, just understand it like that, right? Then, of course, when we say if the enthalpy of the products is less than that of the reactants, we know that the change in enthalpy will be negative. And if the change in enthalpy is negative, we know it's because the products have got less energy uh, than the reactants. But where has that energy gone? It's been lost to the what? To the system. And remember, when the system loses something, a negative sign is put to show that something has been lost from the system. And so when the enthalpy change is negative, that reaction is what? That reaction is exothermic. Okay, so that's pretty much about enthalpy. So before we can talk about calorimetry, let's look at this particular example so that we can be able to appreciate something. So we are saying when one mole of methane is burnt at constant pressure, uh, 890 kilojoules of energy is released as heat. So released as heat. So is that going to be a negative value or positive value? Can someone respond? Okay. Yeah, exactly. So it's going to be negative, right? Because energy has been released. Okay, energy has been released. Yeah, so you see, like for these topics, they are relatively interesting and easy once you just understand the concepts and you realize that, like from what we've been doing, you realize that there is nothing to memorize here, right? Yeah, I'm sure you may have noticed that there's nothing to memorize. You just have to know, and once you know, even after a long, long time, you'll be able to recall because that's something you've. And even more importantly, even under the pressure of an exam, you don't make mistakes. Huh? So they're telling us that one mole of methane is burnt at constant pressure, and 890 kilojoules of energy is released as heat. calculate the change in enthalpy for a process in which a 5.8 gram sample of methane is burnt at constant pressure. So here, what you are basically looking, this is really more of an analytical than really solving. Like we're not really using the formula yet, but we will use them later on. But here is just for us to understand really the more concepts better. So what they are telling us is when you burn, and let's just delete this. So they are telling us that when you burn one more of methane, what you get, this amount of heat is released, isn't it? Is released. Huh? So now they're saying they then burnt 5.8 grams of methane. So then how do we find the what? How do we find the enthalpy change? So now take note, here they've given us the heat. Here they've just given us the heat, right? But they've said something that's interesting. They've mentioned that constant pressure. And we know that at constant pressure, what happens? The heat of a reaction is equal to the what? Is equal to the enthalpy. Okay, so please know this concept. The enthalpy change is equal to the heat at constant pressure. So the change in enthalpy is equal to the heat at constant pressure. Okay, so here this question is talking about constant pressure, but we know one more of methane produces that amount of heat. So we know that one more of this methane, when it undergoes this reaction, what we are having is there is the enthalpy change of that, right? Now we've been given that mass. So what can we do with this mass? We want to find the number of moles of methane in that mass, and then we're just going to relate this mole, the amount of heat released from one mole, and the amount of heat released from that mass, and of course the moles that will calculate from that. And once we've got our heat, that's going to be our what? That's going to be our enthalpy change. Okay, so that's not too complex now, right? Okay, so now we say how do you find number of moles? So moles is going to be mass, sorry, mass. So the mass is 5.8 grams over the molecular mass, right? Okay, so it's going to be that gram per what? Gram per mole. As for the molar mass, so the grams cancel, we're remaining with the moles. So the moles are going to give us what? 0.36 moles of methane. Okay, so 0.6 moles of what? 6 moles of methane. So once we have that, then we now say, okay, so if one mole of methane gives us this, then how about 0.36 mole of methane? What is it going to give us? So yeah, so that's basically how we are looking at it, right? So that's how we are looking at it. So what do? You are multiplying, right? Cross multiplying, that's to say. So let's just write this so that our units can cancel. So I think I did okay, let's just write this. Okay, so maybe we can remove this methane, let's just remain with this. So we have yeah, so we have that, and then we have 890. So that's negative 320 what kilojoules. And this makes sense because this the number of moles 0.36 is less than half of a mole, right? And even the energy that we are getting is less than half of what of that amount what that's released when a mole is bent. So now we know. So what we found is the heat, but of course we know that at constant pressure the heat is equals to what? To the enthalpy change. Therefore, the enthalpy change is so the enthalpy change is that. So that's basically how you do with this question. So you see, it's a very very relatively straightforward topic. The key thing is the same way we started with the fundamentals. We are just building on them, and you see it becomes easy to follow. So let's now talk about calorimetry. So we've talked about that now. So for calorimetry, what we are basically trying to determine is the energy associated with a chemical reaction, right? So yes, a reaction has taken place, but then we want to know what amount of heat has actually been produced or has been absorbed. Okay, so you're basically trying to say what is the heat associated to with that chemical reaction. So the device that we use is a calorimeter, and so calorimetry is the science of measuring heat based on observing the temperature change when a body absorbs or discharges energy as heat. So what basically happens, and the other thing is that substances respond differently to being heated. I'm sure we discussed something in biology about where we said water has got a high specific heat capacity, right? So meaning you need a lot of heat for you to raise the temperature of water, and water has to lose a lot of what? A lot of heat for its temperature to change. So now there are two terms which are very important for you to understand and differentiate. Is specific heat capacity is the energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay? Then molar heat capacity is the energy required to raise the temperature of 1 mole of a substance by 1 degree Celsius. So you see the same thing, but where is the difference coming in? The difference is coming in that for molar heat capacity, we are talking about raising the temperature of 1 mole of a substance, whereas for specific heat capacity, we are talking about raising the temperature of what? Of 1 gram of a substance, right? So please take note of that. So of course, there are many expensive ways in which you can determine the heat associated with a system or associated with the chemical reaction. But for academic purposes, the one that we usually use is what we call the coffee cup calorimeter, right? So there are certain times where I remember there used to be a tutorial sheet question where they would say, draw a coffee cup calorimeter. I don't know whether your tutorial sheet has got one question like that. So basically, it's about two styrofoam cups with a cover in which a stirrer and the thermometer can be inserted. So it's called a coffee cup calorimeter because I'm sure you may have seen when you go to a shop, you go and buy coffee. Yeah, you have more or less a cup like that, or even I'm sure I've seen those coffee cups, right? Like they're like a juice bottle, but not a juice bottle, right? But they're just shaped like one. But you use to put hot liquids, coffee, and things like that. So yeah, they take that shape, and then the fact that those things usually have like a small opening on top to ensure that whatever you've put in there, especially the coffee, doesn't grow cold, doesn't go cold before you take it. So the outer cap is used to provide extra insulation, but really the key thing that provides insulation is the styrofoam caps. So you've seen those two things there. You've seen that there are two layers. So there's a styrofoam caps, but then there's also the outer cap used to provide extra insulation. The inner cap holds the solution. So those styrofoam cups, right? There are two. The inner one is to hold the reaction, is to hold the solution in which the reaction occurs. The outer one is to provide extra insulation because you can never be too sure, right? So this kind of calorimeter that we are talking about, or the one that is being shown there, the coffee cup calorimeter, it's an example of a constant pressure calorimeter. Reason being is that the atmospheric pressure remains constant throughout the process. So there is nothing like you compress the cup, okay? So there is nothing like you compress the cup, or you add pressure to the cup. You're just using the atmospheric pressure, right? The air the pressure around. So it's a constant pressure calorimeter. That's why we can be able to relate the heat that we are going to get from this reaction. We can be able to convert it to the what? To the enthalpy change. Why? Because remember, heat is equal to enthalpy change under what conditions? Under constant pressure, exactly. So that's something that's important there, right? So if two reactants at the same temperature are mixed and then the resulting solution gets warmer, then what are you thinking? You are thinking it's what? It's an exothermic reaction. So then you know which sign you are going to assign. Okay, that seems okay. Yeah, so you know which sign you're going to assign to what? To that enthalpy change. So yes, that heat is there, but you have to assign a sign. You have to give it a sign. So you say, okay, so the sign is. But usually, as you will see, the formula really pretty much does that for us, huh? Does that for us. But it's good to have that understanding. So, and then if you get two reactants at the same temperature, and then you see that as the reaction proceeds, it gets cooler, huh? So the reaction mixture gets cooler. So then what's happening there is an uh, mm, okay, so let me just repeat that. So if the two reactants at the same temperature mix and the resulting solution gets warmer, it means that there is heat, which is what? Which is being produced. Then if the reaction if the solution cools, it means that it's an endothermic reaction, meaning whatever chemical reaction is occurring is requiring the what? The energy of the solution, right? So because it's requiring the energy of the solution, so the solution is going to get cooler. Yeah, that's what I wanted to explain. So that's basically what those notes on your right are explaining. So now let's now relate how we can be able to find all these things based on our styrofoam, on our coffee cup calorimeter. So uh, we also need to know the heat required to raise the temperature of a given amount of water. So of course we know the specific heat of water. So for these questions you have to know the specific what? Specific heat capacity of the of you know to raise the temperature of the solution of what in which the reaction is in, okay? Because that's going to give you an idea, because you can imagine if you are using something that has a different specific heat capacity, you can get pretty wrong answers, huh? Yeah, so you always want to know so that you can note, okay, and you standardize it, right? So that when you compare it with something else, okay, so this reaction produces more heat because we're using, and water is the best to use, because remember, like we discussed in biology, to say water is a good solvent, so many reactions are able to go in water. So you using water and its and specific heat capacity is more standardized because it's the most common solvent that we use, isn't it? Okay, so specific heat capacity of water is 4.18 joule per degrees Celsius. So it means that it takes, or rather, we could say 4.18 joules of energy is required to raise the temperature of 1 gram of water by 1 degree Celsius, right? So now, what do we know about this is that the energy that's going to be released by the reaction is the energy that's going to be absorbed by the solution. Let me repeat that. Remember that this is a cup which is insulated, right? So no heat, or we are assuming no heat is leaving this cup, isn't it? So it means that the energy which is released by the reaction as heat, it's absorbed by the solution, isn't it? So what happens is that as the reaction is releasing heat, the solution is gaining that heat. So then the temperature of the solution is going to begin to what? Is going to begin to increase. But then you don't want to be biased. It also depends on the mass of the what? On the mass of the solution. Imagine, we would imagine that the differences in the increases of the temperature is going to be dependent on what? On the solution. You can imagine warming water on the stove, in a small pot and a very big pot. The rise in temperature in maybe 30 minutes will be different, isn't it? So that's why we consider the mass of the solution as well. And of course, the increase in temperature is important, because of course, so for this example, we're talking about an exothermic reaction. Then the specific heat capacity is also important, because we know to say, oh, okay, so this amount of, energy is what's required to change the temperature of this particular substance by this margin, right? So you want to get that, right, right? So that's about it. So now, so like for instance, we are now saying, okay, so there was this particular equation or reaction where there was an increase in temperature. So the final temperature was 31.9 degrees Celsius, and we started with pretty much 25 degrees Celsius. So the difference was what? 6.9 degrees. So just from that alone tells you that what kind of reaction is this? I was expecting someone to answer. So that alone tells you that this is an exothermic reaction. Okay. Then the mass of the solution is what? The mass of the solution is 100 mUs. So of course we can remember, uh, density. Okay, so we can always use density to convert volume to what? To mass, isn't it? So we say mass is equals to density times volume, isn't it? Which is pretty much what has been done there. Okay, so it's got 100 grams. So there we have everything. So we've got the specific heat capacity, and you see they've written all the units properly there, and the units are cancelling properly there, and you see you are getting that heat. So now, so that's now what's important here, right? Now you see this heat that has been produced, we are not really sure to say what amount what amount of solutions has been produced. So how much energy would have been released if twice these amounts of solutions had been mixed? So now we are trying to assign, to say, okay, what amount of heat is going to be produced per mole of the reacting substances, right? Because no, we always want to deal with moles, because it's the moles that we use to then know to say, okay, you know what? When I want to do this reaction and I want to produce this amount of energy, I have to use what? I have to use this amount of moles. And when I want to do this, I'm going to use this amount of moles. So we'll just quickly wind up on this, so that when we come back, we'll just look at examples, so that at least like that will move a little bit quicker, right? Yeah. So let's just wind up this, right? So now the answer is that twice as much heat would have been produced, right? The heat of of a reaction is an extensive property, so it means that it depends directly on the amount of substance, in this case on the amount of reactants, right? uh, an intensive property is not related to the amount of a substance. For example, temperature is an intensive property. So here what they are basically saying is that with regards to heat, it depends with the what? It depends with, so the heat of a reaction is an extensive property, meaning it's dependent on the amount of of substance. And this makes sense, right? Because if you get let's say two charcoal pieces, right? And you light them up on the brazier. You don't, or maybe let's say you put maybe, or maybe you put maybe, or you cover the brazier maybe with half the needed amount of charcoal. The heat produced won't be as much as if you cover the entire brazier with what? With charcoal, right? So heat is what? Is an extensive property because it's dependent on the amount of the reactants, right? But temperature, on the other hand, is what? Is an intensive property. So what this basically means is temperature is something that a substance is going to have, right? It's something which doesn't increase dependent on what? Dependent on the amount. So, but anyway, the take-home message is that the heat of a reaction is an extensive property. Therefore, we always want to quantify with regards to moles because we know that depending on the amount of substance that we have. And what we know, moles is what? Moles is simply amount of substance, right? So we have to relate this energy that has been released. We want to quantify it in what? We want to quantify it in terms of moles, okay? So enthalpies of reactions are often expressed in terms of moles of reacting substances. I've explained why. So the number of moles of hydrogen ions consumed in the preceding experiment is what? So yeah, so you see there they're just trying to convert that 50 mils to liters, isn't it? So they are just trying. So we are using that's the formula in case you forgot. They are just using the concentration formula to find the number of moles. So they are saying the concentration is one molarity, so it's one molarity, right? So it's one moles per liter of hydrogen ions, right? And the volume was what? Was 50 mils. So we are dividing it by 1000 mils to convert to what? To liters. So we know that those were the number of moles of hydrogen ions which were used in this reaction. So then what then we are saying is, remember what we solved, that heat that we solved. So then we are saying, uh, if that heat was released by this number of moles, then what would be the heat produced by what? By one mole. So it's almost as though we are saying, uh, okay, so we are saying that 2.9 times 10 3 joules was produced by what? Was produced by 0.2 moles of what? Of hydrogen, right? Of hydrogen ions. Then we're asking to say, mm, what then, what amount of heat then will be produced by 1 joule? Sorry, by 1 mole, pardon me. Isn't it? So 1 mole. So we are saying, so it's going to be X. So it's going to be X. Then that's going to be 5 minus 2 more. And then it's going to be, sorry, cross multiply basically, right? So it's going to be 2.9 times 10 power that joule over 1 more. So you just divide that. So I just wanted to show you how, why they divided what they divided there, right? So you see that what they've divided, that's why I've used this so that people can see what they really divided, right? So you see what they've divided. So that those are the moles, those are the moles. So so, but the take home point, the take home message is, see that this is what they divided here, right? So this was what they divided, and so what they get is the amount of energy or the heat which will be produced by what? By 1 mole of the hydrogen ions. Okay, so that's very very important. So now what then we have is very crucial, because then now we know to say, if I've got these amounts of moles, I know that the amount of heat which I'm going to produce from this reaction is going to be this. And that's the beauty of writing the enthalpies in that format. So we are just remaining with this last part. then we are done. I wanted to ensure that at least we finish this, so that we don't start from the middle and then we have we have misconceptions. So so that's the amount of heat, the one that we saw there. So that's the amount of heat which is released per 1 mole of hydrogen ions neutralized. So we see from there now. So that was that. So that was that, and then we can. So since that was joules, so you can convert it to kilojoules. It's going to be about. So that was about 50. That was 58,000, right? About 58,000 joules per mole. So we convert it just to make it better. So we just say 58 kilojoules per mole, so that at least it's shorter. So now, since we know that energy was released, so what are we going to say? So we put a negative there, you see. So the enthalpy change is negative 58 kilojoules per mole. Notice that in this example, we mentally keep track of the direction of the energy flow and assign the correct sign at the end of the calculation. Okay, so to summarize, we have found that when an object changes temperature, the heat can be calculated from the equation specific heat capacity times mass times the change in the temperature. Note that when the change in temperature is positive, heat also has a positive sign. So it means that the object has absorbed heat, so its temperature increases. So really that's about it, right? So this is thermochemistry. So it's just just keep building, building and building. So next week, sorry, not next week, next time we meet, we'll look at this particular question, and also as well as other questions, and then we'll see how we can be able to appreciate these things. So are there any questions?